Welcome to this course on computational mathematics with Sage Math. In this lecture, we will explore some more concepts in linear transformations using Sage Math. So, let us start with a problem. So, the problem is as follows. Suppose T is a linear transformation from Q3 to Q3 given by T of V1 is equal to W1, where W1 is 2, 1, 1. T of V2 is equal to W2, where W2 is minus 1, 1, 3, and T of V3 is equal to W3, where W3 is 1, 2, 4, and V1, V2, V3 is a basis where V1 is this vector, V2 is this vector, and V3 is this vector. So, you are defined a linear transformation T on a basis vectors V1, V2, V3, and we know that a linear transformation is completely determined once we define it on a basis vector. So, our job is to find T explicitly. That means we want to find how T of x1, x2, x3 should look like. And once you have obtained this, then find let us say image of any vector, and then suppose you have a basis C which is equal to this, and then you have basis B of Q3, then find matrix of this linear transformation with respect to basis B and C. So, once you have obtained T, then finding basis will be easy, because these kind of problems we have already come across, how to find matrix of a linear transformation with respect to arbitrary basis. So, our main task is to find T explicitly. What do I mean by that? Here what we mean is T of x, if x is x1, x2, x3, should look like something like this: a11 x1 plus a12 x2 plus a13 x3, and so on. And this we can write as x1 times column vector a11, a21, a31 plus x2 times column vector a12, a22, a32, and x3 times column vector a13, a23, a33. If you want, you can write x1 times a vector A, x2 times vector B, x3 times vector C. Right. So, let us see how do we find this a11, a21, a31, and so on. Okay. So, how do we find this? So, let us say T of x. Now, x is, let us say, x1, x2, x3, then we can write x as x1 times e1 plus x2 times e2 plus x3 times e3, where e1, e2, e3 is a standard basis of Q3, right. So, since T is linear, T of x will be x1 times T of e1 plus x2 times T of e2 plus x3 times T of e3. Now, do we know T of e1? We do not know. But what we know is T of V1, T of V2, T of V3. However, this V1, V2, V3 is a basis of Q3. Therefore, any vector can be written as linear combination of V1, V2, V3. So, in particular, we can write E1 as scalar linear combination of V1, V2, V3. So, suppose let us say E1 is equal to A1 times V1 plus A2 times V2 plus A3 times V3, and then T of E1 will be A1 times T of V1, A2 times T of V2 plus A3 times T of V3, which is A1 times W1 plus A2 times W2 plus A3 times W3. Here what are A1, A2, A3? A1, A2, A3 are the coordinates of E1 with respect to basis V1, V2, V3. Right. Similarly, we can find T of E2, and T of E2 will be B1 W1 plus B2 W2 plus B3 W3, where B1, B2, B3 are coordinates of E2 with respect to basis B. Similarly, we can find T of E3. So, our main task here is to find coordinates of E1, E2, E3 with respect to basis B1, B2, B3, and that is it. And after that, we can find out T of E1 as this T of E2, T of E3, right. Okay. So, let us see how we can do this in Sage. So, first let us declare x1, x2, x3, x3 as variables. One way to declare this variable, we can declare individually, or you can declare x is equal to sr dot var, and x is a variable, so inside single quote, and 4 denotes here this x will be x0, x1, x2, x3. So x0 is actually the first component of this tuple. So if I say x of 0, this will be x0 and so on, right. So that is your the variables x0 to x4. Now let us look at let us declare v1, v2, v3 the basis of the domain, and write B as list of v1, v2, v3. Okay. Similarly, the images w1, w2, w3 let us store in a list capital D. Next, let us define E1, E2, E3 as the standard basis of Q3. So this is over QQ, you can write it, it's not necessary. This E1, E2, E3 are the unit vectors. Okay. Next, let us find the coordinates of E1 with respect to basis B. How do we do that? So first let us declare V and W as domain and codomain of T. In this case, V and W are the same, so that, and it is equal to Q3. And let us say V1, capital V1 is equal to the subspace of capital V with B as basis. So that's a capital V1. Now how do I find coordinates of E1 with respect to basis B? So all we need to do is we simply say capital V1 dot coordinates, and in the bracket write E1, and let us store this in A. So first component will be A1, second component A2, A3 and so on, right. So this is your A1, this is your A2, this is your A3. So we have found out A1, A2, A3. Once we have obtained A1, A2, A3, we know what is T of E1. Similarly, let us find out B, the coordinate of E2 with respect to B. Similarly, let us find coordinates of E3 with respect to B. So once we have found the coordinates of E1, E2, E3 with respect to the basis V1, V2, V3, let us define T of E1. What will be T of E1? The first component of the coordinate of E1 with respect to B times W1, which is the first component of D, and so on. So add all this will get you T of E1. That's the T of E1. Similarly, let us find T of E2 and T of E3. So once we have obtained T of E1, T of E2, T of E3, then we can find out the F, which is x1 times T of E1 plus x2 times T of E2 plus x3 times T of E3, and that is what we had here, x1 times T of E1, x2 times T of E2 and x3 times T of E3. So that's the components of the linear transformation. Let me show you this as a column matrix. So this is your first component, second component, third component. So we have found T explicitly. Once we have found T explicitly, let us find out whether T of E1, T of V1 is W1, T of V2 is W2. So how do we do that? First, now let me declare a linear transformation with these as images. So let us say G of x1, G of x2, G of x3 is list of F. This is the list, and then define a linear transformation T from V to W with this image as this G, and let us, okay, so that's the linear transformation. Now let us check whether T of V1 is it equal to W2, T of V2 is equal to W2, and T of V3 should be equal to W3, and the answer is true. Then we also wanted to find the image of T of 3 comma minus 2 comma 5, 3 comma minus 2 comma 5. So let us find that quickly. This is quite easy. I am sure you all of you by now know how to do that. So we will declare a vector, let me say U is equal to vector over QQ, and in the square bracket write its coordinates 3 minus 2 5. So that's the U, and then let us say T of U, T in the bracket U. That's the image. Okay, so we have solved this first part of this problem. The second part is to find the matrix of this T with respect to basis beta on domain and C on codomain. So that is easy. I leave that as an exercise for you to do. Okay. Now let us look at next problem. If you have two linear transformations, you can take its composition. Of course, it should be compatible. Similarly, you can define sum of two linear transformations. So composition, how do we define? So suppose, let us say T is a linear transformation from R4 to R3 and S is a linear transformation from R3 to R4. Then the composition S composite T makes sense, and it will be a linear transformation from R4 to R4. It is easy to check that if you have two linear transformations T and S, then S composite T is also a linear transformation. That's a very simple exercise. Similarly, you can check that T plus S will also be a linear transformation. In this case, T plus S will not make sense, but if T and S are both linear transformation from, let us say, V to W, T plus S will make sense, and T plus S will also be a linear transformation. So once you have a linear transformation S composite T, then let us find matrix of this composition, let us say with respect to standard basis, and then we want to check how is this matrix of this composition of linear transformation related to matrix of T and matrix of S. So that's the result says that if C is the matrix of linear transformation S composite T, and if A is a matrix of T and B is matrix of S, then C will be B times A. That's the results. That is the third part. So this is what we want to check. Now here we are doing everything with respect to the standard basis. However, the same result will be true with if you take any basis on domain and codomain of T, similarly on the codomain of S, right. So let us look at how we can solve this problem. This is quite easy. So first let us declare S and T as linear transformations. So first let us declare x, y, z, w as variables. F of x, y, z is the first linear transformation T, g of x, y is equal to second linear transformation, that is S, and let us define T to be linear transformation from Q4 to Q3 and with image as F. Similarly, S as linear transformation from Q3 to Q4 with image as G. So once you have declared S and T, now let us declare let us find matrices of T and S with respect to standard basis. So we can simply say capital A is equal to T dot matrix, side is equal to right. Similarly, B is equal to S dot matrix, side equal to right. So that will give you the matrices of T and S with respect to standard basis. Now let us declare the composition. The composition of S and T is nothing but S star T. Similarly, the sum will be S plus T. Now let us find matrix of this U, which is S composite T with respect to standard basis. So this matrix is this. Here you can also print what are these matrices A and B. Now let us check whether B into A is equal to C. That is what we wanted to prove, and the answer is yes, it is true. The matrix C is nothing but product of B and C, and of course you should explore the same thing with respect to arbitrary basis on domain and codomains of S and T. So that I will leave it as an exercise. This is quite simple. Okay. Now let us look at one more thing. Suppose we want to we have already seen how to find matrix of change of basis. If you have two bases, then of a vector space V, and if you take any vector, then we can write its coordinate with respect to the two bases, and we have seen that the two coordinates are related by a matrix. There is a relationship, and that relationship comes from what we call it change of basis matrix. Okay, so this we have already seen. However, this change of basis matrix can also be obtained as follows. So you look at a linear transformation which is identity linear transformation from V to V, and write matrix of IV with respect to basis B and C. That matrix is nothing but matrix of change of basis from B to C. So let us look at this. So suppose we take the space V is equal to Q to the power 4 and V1, V2, V3 as a basis of this, and let us define W1 to be a subspace of capital V with B as basis. Similarly, let us define a basis W1, W2, W3, W4 of V, and define capital W2 to be the subspace of capital V with respect to C as a basis. And then we know how to find matrix of change of basis from B to C. We have already done this. So let us just recall that how we did. So the matrix of change of basis from B to C can be obtained as the column matrix of the coordinates of V1, V2, V3, V4 with respect to basis W1, W2, W3, W4, and this is this matrix. This actually in the problem I had denoted this by IBC. So let me declare this as IBC. Right. Once this is the matrix of change of basis. Now what is that we want to show? We want to show that this matrix is nothing but matrix of the linear transformation, the identity linear transformation from V to V with respect to basis B on domain and C on capital domain, on codomain. Right. So let us do that. Let us look at. So declare variables V1, x1, x2, x3, x4, and identity map ID x1, x2, x3, x4 is x1, x2, x3, x4 as a list, and declare S as a linear transformation which takes from W1 to W2. Remember, this is with respect to basis B1, B on domain and C on codomain. That is why here V1, W1 and W2. You could have declared this from V to V, and then you could have restricted S to domain, the basis B and C on domain and codomain. Right. Okay. Now let us find the matrix of S with respect to these two bases, and this is this, and you can see that these two IBC is same as matrix of IV with respect to basis B and C. So that is what we have proved. Now let us use this to look at what happens to matrix of a linear transformation when you change the basis. Okay, so you have a linear transformation, you find its matrix with respect to a given basis. Now you have another set of bases on domain and codomain, and then find matrix of that same linear transformation with respect to the two new bases, and then we want to check how are they related to each other. Okay, so let us see how are they related. So let us start with a problem. We have a linear transformation T which is from R3 to R3 given by this components, and let us fix a basis B1 of T and B2 B1 of the domain of T and B2 of codomain of T, right? And let us assume that rho 1 is the linear transformation that takes standard basis to B1, and rho 2 a linear transformation that takes standard basis to B2. Now suppose let us say capital A is the matrix of T with respect to standard basis. Now we have two bases beta 1 B1 and B2 on domain and codomain. So let us say capital B is the matrix of T with respect to basis beta 1 B1 and B2, and then we want to check how are these A and B related. So this A and B are related by this relation rho 2 times A. Rho 2 is the matrix of the change of basis from standard basis to B1, and rho 2 that is the rho 1. Rho 1 is the matrix of change of basis from standard basis to B1, and rho 2 is the matrix of change of basis from standard basis to B2. So this is how they are related. A and B are related. In particular, you can write this as rho 2 inverse times B rho 1 is equal to E. So in this case, actually one can if you have A and two matrices A and B which are related by this relation, we say that A and B are similar matrices. So the matrix of T with respect to different bases are similar matrices. That's what we are proving. Okay, so let us work out this. So suppose you start with V and W, which in this case both are Q3, and let us define the linear transformation T with given expressions as a list in F. So that's the matrix, that is the T, and let us define the matrix of T with respect to standard basis. Let me call that as A. Similarly, let us find let us look at the basis B1, which is U1, U2, U3. You can check that this is a basis. This is a basis. Similarly, take B2, a basis which is V1, V2, V3. Again, you can check that this forms a basis. We need to check that B1 and B2 are linearly independent. I have already checked that they are bases, so I don't need to do that. But when you take arbitrary vectors and you want to form a basis, you must check that it does form a basis. Now let us say capital V1 as a subspace of V with respect to basis B1, and W1 as subspace of V with basis B2. Okay, so this, let us run this, and once you have run this, then let us now restrict T to this basis V1 and to subspace V1 on domain and W1 on codomain. So that means we are finding now linear transformation with respect to the new basis. So and that matrix of T2, which is T restricted on domain and codomain, let us call that as B. So that's the matrix B. We have found what the matrix A over here. That's the matrix somewhere we calculated. Yes, this is the matrix A, which is with respect to standard basis. Now we have calculated matrix B with respect to the basis B1 and B2. Now let us look at let us find row 1 and row 2. What is row 1? Row 1 is the matrix of change of basis from standard basis to B1. So how do we obtain? Just now we saw that we can obtain that as a matrix of identity linear transformation from V to V, and with respect to basis, standard basis on domain and basis B1 on codomain. So let us define a linear transformation with identity as image from V to V1. V1 is subspace of V with basis B1. So let us find row 1 and matrix of row 1. That's the row 1, that is the change of matrix of change of basis from standard basis to B1. Similarly, let us calculate matrix of change of basis from standard basis to B2. This is row 2. Now let us check what we wanted. We can check that B times row 1 is equal to row 2 times A, and the answer is true. Or we can check that B is equal to row 2 times A times row 1 inverse. So we have verified what we wanted. Okay. Now here we have taken a standard basis for T, and then we change to basis B1 and B2. You could start with B1, B2 on T and take another basis, let us say D1 and D2 on domain and codomain, and then also you can explore this relation. So that I will leave it as an exercise. Okay. Now let me leave you with 3 simple exercises for you to practice. The first exercise is find row space, column space and null space of this 4 cross this is 7 matrices, 4 cross 7 matrices. And second problem is to consider a linear transformation T from R4 to R3 with these as components, and then take arbitrary basis on domain and codomain and find its matrix with respect to arbitrary basis, and also verify rank nullity theorem for this. And similarly look at the third problem. This is actually I already said that as an exercise, the linear transformation, you are given a linear transformation from V to W, find its matrix with respect to two bases beta 1 and beta 2. Similarly, find its matrix with respect to another two bases C1 and C2, and then find the relationship between the two matrices which you have obtained. Okay. So, these are the three simple exercises. Let me stop here. In the next class, we will look at how to deal with eigenvalues and eigenvectors, and it as you know, these eigenvalues, eigenvectors have numerous applications in linear algebra. So, we will see you in the next class. Thank you.